Okay, hi. Good morning and welcome to lecture 9 of Quantum Physics for Non-Physicists, and today is the 13th of October. So, today we will continue with the last lecture, and if you watch the last lecture live, then the recorded version is a bit different, although it's still more or less the same content, and I will recap what we did first. So we will continue with the Stern-Gerlach experiment because it's a good field in which to explore like different types of Hamiltonians and what the measurement means and how we can implement the measurement in quantum mechanics physically. Okay, so today we will talk about interaction Hamiltonians. So last time we talked about non-interacting systems, and today we'll talk about interacting Hamiltonians. We'll not talk about the thing that's actually happening in the Stern-Gerlach experiment because we don't have all the background needed for that, but we'll give another example of something that is used or that is the ideal interaction Hamiltonian for measurements in general, which couples some observable that we want to do to something that we can actually measure, like the position of a particle. So we'll look into this, and then we'll look into one specific implementation of this called the modular momentum, because this will also be useful to analyze many other experiments like the double slit experiment, which we'll do soon enough. Okay. So our daily analogy today is that doctors do not treat themselves in the same way that lawyers do not represent themselves. If a doctor is sick, he goes to another doctor. If a lawyer is in trouble, she will hire another lawyer to represent her. And what I mean by this is that, of course, the doctor knows that they themselves are a human body which can get sick, and which they could treat in the same way that they treat anyone else. But it's just so cumbersome to try to treat yourself as this physical object that you just don't do it. You just go to someone else who can look at you and say, okay, yes, I see a patient, and I can completely disconnect this patient from my inner reasoning, and that therefore I can treat them well. In the same way, as physicists, we know that if we take quantum physics seriously, then we ourselves, we have physical bodies, we're also quantum systems ourselves, right? So in a measurement like we saw a long time ago, what happens is that we are getting entangled with the thing that we'll measure, and we'll see more about this today. Okay, so in the end, it's like we ourselves are in a superposition of seeing one outcome and seeing the other outcome. But we just don't have the tools to treat ourselves as physical systems in this way. Right? We don't have the tools to reason about this. So we just make this artificial cut and say, at some point, I know that everything is unitary evolution, but at some point, for practical purposes, I say, well, from here up, I just treat systems as classic. I treat myself as a classical system. And I say, oh, from here up, it's just a measurement, which is this projection, okay? Which is not a unitary evolution. And we know it's not the truth that is actually happening. We know that we are physical systems ourselves. We know that everything is unitary, but it's just a cut that we do for sanity, and so that we can actually reason about the outcomes we get. There are some problems with this, as we might see towards the end of the lecture or in one of the exercise classes, that if we treat everything else as quantum systems but ourselves as classical, we may reach some contradictions, okay? Because it's an artificial cut. But this is called the Heisenberg cut. It's very famous, and it's the same way to do it. Okay, so housekeeping. First thing is, because the pandemic is getting much worse in Zurich, we will no longer have the question and answer sessions in the alumni lounge. It's also a bit too cold to sit outside. So for now, we'll be on Zoom in the afternoon, so you can come to Zoom anytime, or you can register. By this I mean send us an email and say, I want to meet in person because I have too many questions or they can't be easily asked online, and then we'll try to arrange a meeting. Okay, good. The other thing is that sometimes when the lectures, I feel like they didn't go too well, then I will record them again. But of course, like the doctor, I'm not the best judge of myself. So if sometimes I might think it's not gone well, but it was because it was too slow, but for you it was just slow enough, for example. So what I'll do is I'll ask you at the end of the lecture if there's something that you'd like me to record again. And of course you don't have to answer, but if you do, then this is helpful. Okay, good. So what we did in the last lecture was to look at non-interacting systems. So we saw in particular this electron that had an internal degree of freedom, then the x coordinate and the z coordinate, and the Hamiltonian was all non-interacting. But so in the more general case, we can have this Hamiltonian being, the Hilbert system being made of tensor product of two systems A and B. And what we mean by non-interacting is that the Hamiltonian has the form of one part that only acts on system A plus one part that only acts on system B. Okay. And what we saw is that in these cases, the evolution, so the the evolution after time t, which is given by th, this is, we can really split it into these two parts, hb or h. Okay, so this was the result. And if we have local observables, we saw that they only depend on the evolution on the side of the system in which they act on their subsystem. So if you have an observable that is something like acts only on system A, then its evolution over time it ends up depending only on the Hamiltonian that acts on A. And then we even went a bit further and we saw that this, of course, this is the U of this average is done by doing U of t of S0 and then putting here the thing. But we saw that in this case, it didn't measure what happened to system B. All that measure was what happened to system A. So that's UA of t. And it may as well have done nothing to system B. MA, HA, translate into T on B. And there's a dagger there. And I can T on B. Okay. So the local, the local observables, they really only depend on what happens to system A, and what happens to system B we could replace here with any unitary, because what would happen is that you'd have the unitary, the transpose conjugate here, so U dagger, and here you have U, and they all just multiply by the identity, so you ended up with U dagger U, which is the identity. So it doesn't matter what you do to system B. Okay, so this was the part that I did a bit better in the re-recording. We also looked at the free evolution of a Gaussian in 2D. So we took a Gaussian that is moving in the y direction only, which means, so these are the stats of the initial Gaussian. So the initial position is x0, and the variance is the sigma. So that's this. So here's x, and here's the wave function square. And the initial moment over x is 0 because there's no qx here. And the initial variance of momentum is given by kind of the inverse of the variance in position. And the same for y, except on y now we have momentum hk because the k is multiplied by y up there. Okay. And so this is kind of the wave function over y for the maximum in x squared. And then we saw this way of looking at the wave function from above, Whereas, so here now we have X and Y, and what we're looking at, like this purple area, is just the way with probability density above some threshold. So it's like we cut it like through the middle of this Gaussian, and it's like just this area here. Okay, so over X and over Y. Good, so it kind of tells us what's the area in which we have a high probability of finding our particle if we measured it. Okay. And there it is. Of course, it has a long tail. And here on Y, on the momentum over X and Y, we know that the momentum over X is 0. So we let it evolve over the free Hamiltonian. And what we saw is that it spreads out with, so quadratic in the inverse of the initial spread, because the sigma is down here and there's a t square. And it spreads out in both directions the same, because we started with the same sigmas for X and Y. This was the choice. It does not move the average X position, but it does move the average Y position by the momentum. Okay, and in the P direction, nothing. In the P basis, nothing happens. Okay. By the way, we could now take this and now say, well, no, I actually want it to also move on in the X direction. This will be needed later. So some kx x. Okay, so what changes? So here we have h bar kx, which means that this thing here gets moved to somewhere like there. Where here it's h bar kx. And then here we get again h bar kx t over mu. And here we get h bar kx, which just means that in the end, our wave function will be somewhere here, where this is x0 kx mu t. Okay, so this is now a Gaussian wave function that's moving with some momentum in the x direction and some momentum in the y direction. And the reason why we're looking at this is because it will be useful for what comes. So let's just recap what we had from the Stern-Gerlach experiment. Okay. So again, the global Hilbert space is the internal Hilbert space of the electron, which is a qubit for spin. And then you have the x position and the y position, right? And the experiment is such that first we start with a Gaussian wave function, that's this one, and the position times something that we don't know in the spin. So in general, it can be represented by alpha 0 plus beta 1, where alpha and beta are complex numbers whose modular add up to 1. Okay, we let it evolve and we just saw what happens. So in this case, it's one that's moving only with momentum in y, and so it just gets spread out more evenly than it's here. And then it will enter some region where there is a coupling to something else, and we'll see what in a moment. And the idea is that in here, we want the wave function to kind of split into two, or to become a superposition of two, one with a momentum moving it to the left, and one with the momentum moving it to the right, depending on the spin of the electron. We'll see this in a moment. And then eventually, because this one is moving there, it will spread out, and it might even have a long tail that even almost touches the other one that goes there. But what would matter is that at some point they hit a screen, which means there may be some photoelectric effect, and we see some light coming out. This is our final measurement. This is where we'll make the cut and say, okay, from here on, it's classic. What we did was we measure the position here in big blocks. And if you find it here, with high probability, we know it comes from this wave function and not from a tail of the other one. So we know that this corresponds to spin being, for example, 0, and here being spin being 1. Okay. The whole point of the experiment is to try to measure the spin indirectly, because we cannot go there and really look at this subsystem directly, but what we can measure is the position of the particle after some time. Okay. So what we did last time was to analyze this region, and now we'll analyze this region here, the interaction region. But we will not use the real Hamiltonian, like I say. We'll just think about what we want and what kind of Hamiltonian would make sense. And then we'll analyze what happens here. Okay. So let's see. Only region B and kind of wishful thinking. Okay, we'll just try to think about what we want. So let's say that the initial state is like we said, so it's going to be something unknown on the spin. Tensor phi 0 of xy, where this will take it to be a Gaussian with some momentum py, and let's say for now nothing here. Okay. And the ideal final state would be to have something like this, like alpha 0 and s tensor. Let's call this phi left on x and y plus beta 1 on s phi right x and y. Okay, where ideally we'd want this to be a Gaussian again. Still moving up. And now with the px being some, let's make it a here. And this one, the opposite. Okay, py minus. The minus or plus signs don't matter so much. We'll do one and then we'll see what signs we end up with. Okay, because it could be that, oh well, actually the one, this one will end up moving to the left and this one to the right, but we'll see about this. What matters is that we want them to end up with, it should be px. We want them to end up with opposite momenta, so that later, even if here we don't distinguish them, even if here we make this region really, really small, and we just have like the two wave functions that in the position basis, they still look the same, but we know that they will evolve after under free evolution. And one is going to go to the left and one is going to go to the right. Okay. So what does this type of transformation remind us of? It reminds us a bit of the C0 in the circuit case. I don't know if you remember. I'll just put here discrete analogy. The C0 gate. So this was this gate. which took a state alpha 0 plus beta 1, say qubit A, qubit B, tensor 0 on B, he took it to alpha 0, 0 plus beta 1, 1. Okay. And I told you at the time that all kind of measurement interactions, they will do more or less this. They entangle the 2 degrees of freedom that we're interested in. So this is what we want. And now we're going to look at the general case. And we're going to see first a way of coupling. So here what we're coupling is the internal degree of freedom with the momentum of the wave function. Okay, the internal degree of freedom with the momentum of the wave function. We will do one that couples the internal degree of freedom with the position of the wave function. So this would be if I just want the position to shift immediately, depending on the value of my spin, and I would just measure it immediately. And then in the exercise class, you'll do how it happens for the coupling to the momentum. Okay. So we'll do the general case first. So we have 2 systems, A, and let's say here X for the position X, and we want to measure something here on A indirectly by coupling it first to the position of B. And so we have some observable A, or before I call them MA, by which I mean that MA, like we saw, it's a sum I, for example, or yes. So in this case, it's like a projective observable. We can make it more general by just putting here whatever vectors. Okay. Good. Let's put I here, sorry, so that it's closer to our example. So this is some basis I of system A. It doesn't need to be a qubit anymore. It could be 3 qubits, for example. It could be an n-dimensional system. It could also be a continuous system. But we have some observable that is like this. Okay, so let's propose the following interaction Hamiltonian. And then we'll see what happens. And this should be Ix, which is just A. Oh, sorry, MA on system A. And here PX. And this leads to the unitary U of t being e to minus a t over h bar ma px. Okay. So now let's see what happens when we apply this to some initial state. So and the assumption is again that the internal and external degrees of freedom are decoupled. This, by the way, these two systems, they don't even need to be the same particle like we had now. It could be some system we want to measure, and then just a pointer, like a pointer particle that we bring in contact with it. So we bring a photon, for example, in contact with the system we want to measure, and there will be some interaction between them. And what we measure later is the position of the photon, not of the thing that, not of this system. Okay. In the case that we saw before, it's happened to be the same physical object, this particle, but it doesn't need to be. So we want the initial state to be, well, something like this one. So this is coefficients Ci. So any state on the system to be measured, we just can expand it in the same basis as the observable tensor. Some F0 of the pointer. Okay. So now, what happens after the evolution? Let's call this whole thing big phi 0 on A in X. So we have E2 minus I t over h bar. And now we have here our observable MA. So that's sum on I, AI, AI, tensor PX. Okay. And now acting on what? On this thing that we saw there. I, Ci, I on A, tensor phi 0 on X. Good. We can put the brackets on the inside like this. Okay, so now we have to see how does this exponential over two things acts there. But the nice thing is that because these things are projectors, the whole thing will become only, so sum over I, Ci, and then we get only I here, and then we get times A minus IT over H bar, and now we get AI PX and phi 0 over X. Okay, so this it will be an exercise in the tutorial. Okay, to prove that this is what's happening. But now we have, so what we have is the sum of the coefficients here, the state I on our system A, and then depending on which state we had here, then something different will happen to the wave function. So it will be acted on with this evolution that is like px times a constant, but the constant depends on the eigenvalue for this I of the observable. Okay, so now we're going to see what is this. Okay, so we have E2 minus I t over h bar, AI, PI. And now because all of these are real numbers, we're just going to give them a new name. Sorry, not PI, but PX. X, which we know because there's only one dimension at the moment. So this whole thing, let's call it just Li. Okay. And so we have this operator that is e to minus I L. We forget now that there's many of them, P. Okay, where L is a real number. And this is what is called, it has a name, and we'll see later why it's called this name. It's the operator modular momentum. So we're going to see how it acts on the wave function. So remember that now it will act on this wave function, which was like a Gaussian, we think. Okay. But we'll see the general case. So well, we know that this phi 0 on x, we can write it in the momentum basis. Okay, so dp wave function of the momentum p. Okay, and this is all system x. For now, I'll drop the subscript because it's the only subsystem we're taking care of now. Okay, so now we have E minus I LP acting on phi 0. Well, this is dp. We can move this thing inside, E minus I LP. Check of P. Right. Okay. And now, well, this thing is essentially a number. Let's see how this thing acts there, how this matrix acts there. Okay. So we have E minus I L P acting on P. And as per usual, we can just do the power expansion of this. So we'll get identity minus I L P plus minus I L squared P squared, check. All of this acting on P. Yes. Well, but we know how the operator P acts on the state P in the momentum basis because it's an eigenstate, right? We know that PP is that small p, right? Because it's an eigenstate. So then what we get here is just identity P minus IL small p, P plus this term. And now P square acting on P, what is it? Well, the first P acts on the vector and gives us the eigenvalue P, and then the second operator acts on it again and gives us again the same eigenvector, so you just get P squared. P, which is just E2 minus IL little p, P. Okay. Good. So we have that I minus ILP acting on 0 dp of, and now we have here E minus IL small p, P. And this is kind of the new wave function in momentum, right? This is the new. let's call it the final wave function. Okay, it's not the derivative. Good. But we want to see, what we want to see is how it, what changes in the position. So what we want to see is how this operator IPL minus IPL acts on the wave function. But what we did was to take the Fourier transform to look at the momentum wave function. Then we apply the thing. And then we saw that we get here the this E minus ILP. Right. And now if we want to see what happens to the wave function in the position basis, we just need to take the Fourier transform again of this. Okay, so we do this. Good, so now we want to see, we take, we want to see what happens to E minus I, big P. L, this is the operator, when it acts on the f of x. Well, this is just taking the Fourier transform of what we just did, so chuk dp E I P x over h bar. And now we have here what we just got, so E I P L, this is the small p, and the initial wave function in the momentum basis, right? Now, because there's an h bar down here, it's more convenient if we work in units of h bar here, so let's just go back, sorry about that. Let's call it, let's take this away. Okay, you can say that if you want. Let's call just this Li, and let's carry the h bar around with us. H bar, h bar, h bar, 1 over h bar, 1 over h bar, all this, h bar. Oh, you let me make mistakes. That's not what I meant. H bar, h bar, h bar. This is inside the brackets. That's inside the brackets. Good. So we'll just put it everywhere there. Good. H bar, h bar, h bar. This is how physicists decide which constants to keep track of. Okay, good. So that's now dp e to I p over h bar, and now x minus L. Right, chuk of p. Well, but now, and our usual constant, 2 pi h bar. Right, 1 over square root of 2 pi h bar. Good. But now, what's inside here? Well, if you look at all of this, this looks just as a Fourier transform of the momentum of wave function, but now instead of putting for a new value of x, which is this x minus L. So this whole thing is just a wave function of x minus L. Okay, which means what? So let's put it here, f of x minus L. That what this operator did in the position wave function was to just shift the whole thing. So let's see if we get the signs right. So suppose this is x, and this is kind of the initial wave function. Okay, let's say this is, it was centered around some x0. Now it goes to the other way. Whoop. Let's put you there. Let's put you there. I think this is the right way around. So we just take exactly the same curve and we just shift it. This is x0 plus L. Yes, right? Because the new wave function in this position should be what the old wave function was in the position in this minus L, right? So even though here is a minus, what it does is it shifts the whole wave function to the right. So this is tach of x minus L. That's it. So what the modular momentum did was to just take the wave function and shift it in the position basis. Good, so now we need to see, well, we started with a more complicated thing. So we started with this thing here, and we want to see now what is happening overall. Okay, so let's copy all of this. Copy. Paste. Go. So now we know that this is sum over I, Ci, I on A, tensor. Let's expand this wave function in the position basis of x minus, our L was TAI, x. No? When the original state was the same thing, which is x. Okay, so what happened was, let's say this is x, and this is the square of the wave function, so the probability amplitude of finding it somewhere. And let's say that the original one was something like this. Okay, so say that this is f0. Okay, and now after this, what we have is kind of a superposition of it being centered around different places. Where this is, so if this was 0, this will be TA1, TA2, TA3, and so on. Okay. So we now have a superposition of this wave functions at different positions, which is correlated with each of them. So it's impossible to draw this properly in 2D. But what you can think is that each of these blobs is correlated with being with the internal state of the system being in some initial state. Okay, it's the things that we wanted to measure. Okay, which means that now if we make a position measurement, so if now we measure this subsystem in a position measurement, then, you know, with high probability, if these things are narrow enough, then we will end up around here. And if we end up around here, then we know that, well, this corresponds to I1 eigenvalue. This corresponds to I2 eigenvalue. This corresponds to I3 eigenvalue. Okay. After the break, we see how to apply this to our spin example, and we'll also see the cases of weak and strong measurements and see the difference between them. So let's take a 15-minute break and see you at 11:45. Okay, let's continue. So what we had before, I'll even make a small animation for you. Wait, you can see this. Is that we start with the wave function over there, and then as time evolves, this animation is going very well. It kind of becomes more. It moves in a way that you end up with all these different peaks, such that if you measure the peak, you know the peak is perfectly correlated with what the spin or the value that you want to observe is right now. By the way, these peaks, I made them here all with the same height, but they don't have all the same height, right? They have different heights depending. So let's make them different heights depending on the coefficient Ci, as we saw up there. Yeah, maybe this one is even smaller. Maybe this one is really big. Okay. So in this case, it was because C3 was much, much larger than C2, which was a bit smaller than C1. Okay. So this coefficients here will tell us, if we square them later, will give us like the amplitude of this wave functions here. So the probability at which we'll measure them when we measure the x position, the probability that it will be here or here or here will depend on CIs, which were, if you remember, the CIs were the initial stage of the system. So we started off with some initial stage like this, and we want to know more about this initial state, so we want to measure it in this basis to find out the CIs. Okay. So if we have, this is even going to be CY squared, and that gives kind of this area under the curve. Roughly, okay, this is not very precise because there could be some interference from phenomena, which we'll look into later, but roughly, okay. Good, so there's two things that could make this a bit less clean. One is, what if t is very small, or these AIs are very small, these labels, then we can end up with something like this. Whoop, whoop, whoop. Oh, maybe make them different sizes. Whoop, whoop, whoop. By which I mean is that there's much more overlap, because here's TA1, here's TA2, TA3. But because the time was small, then this distance here, this distance is smaller, which means that now there's more overlap, which means that when we measure, we're not so sure that what it corresponds to the part of the wave function, to this one where we measured A1, or to this one where we measured A2, for example, if we end up here in the middle. Or we could have that the initial wave function is very spread. Okay. Let me make this even smaller. Get it out of the way. Here. In this case, what I mean is that instead of starting with this one like this, we started with a state that maybe still a Gaussian, I don't know, but it's more spread out. So then we can end up with something like okay, where again there's a lot of overlap between the wave functions corresponding to different outcomes, which means that now again, if I measure the position and I get this outcome, then I say with high probability it corresponded to the first outcome in the system of interest. But if I end up here, I don't really know if it's from there or from there. Okay, so in this case, we say it's a weak measurement, and there's a lot of research into this. At first, you could think, well, why would you do this? Because if you want to gain some knowledge about the thing you're measuring, you want it to be as clear as possible. So you'd want to be in a case more like up here. But the problem is that this now, you disturb this. The state became very, very different from the initial state. Whereas if it's very spread, and we make the time short and things very spread, then you end up with something like this, which is closer to the initial state. There's a trade-off between disturbance of the state and how much information you get off of this. And there's a whole field of research into this, which we'll have a course in the next semester to explain. But just so you know, kind of the idea is that up here we have a strong measurement, meaning if you measure the position, this is essentially equivalent to measuring your observable directly because it's perfectly correlated, there's no overlap. In this case, you're not really sure. And in this case as well, for a different reason. Okay, good. So now we want to, this was a general case and we want to apply it to our spin. So remember, our problem was trying to find what this interaction Hamiltonian was. And for now, let's forget about the y-coordinate and just think of the initial state. Again, alpha 0 plus beta 1. Yes. And here's some phi 0. Okay. We can leave it here for now, but we don't want it so much. Okay, good. So, so first of all, if what we want is an evolution into alpha 0 phi left plus beta 1, right, of any sort. Yes, I can put the y here. Then what is the observable of interest? Well, we want, it's an observable that just distinguishes between 0 and 1. So we take, for example, the observable z. We don't want to measure the x component of the spin because then this would give us a different decomposition, a different breaking into superposition. So we take ms is going to be just z, which is, if you remember, 0. Oh, hello. 0 minus 1 in s. Okay. And because I don't know by how much we want to shift things, we just put here a little gamma. Okay, which is just some constant that we'll decide later what we want this to be. So now let's suppose that the wave function here is just one dimensional. So now we forget about y and we take just x. and we say f0 of x is something dx I of x x, where this could be the, for example, the Gaussian that we saw. Okay, so now we just want to apply this Hamiltonian, which of course is not the real Hamiltonian because we z on s times x. Okay, let's do this one first, and then we'll see that this doesn't work. Of course, this will never be the total Hamiltonian because if you remember, there's still the Hamiltonian of the free particle, just from the fact that it has some mass. It still has this p squared term, but now we say, well, this is maybe much, much larger than that. For example, we just do an approximation where we say, well, let's say what happens if this is a total Hamiltonian. Then if we just apply this, okay, then we get that e2 minus I h over t over h bar, sorry, e minus I t h bar gamma z px applied on our state. Of s on x, which is this thing. S and x. So we get the two. Note that this is our, this is our A0, and minus gamma is our A1. For our observable. So then we really just apply this formula here. Oh, we can even do it extensively. And because the sum only has two terms, we can do it one by one. So we had the coefficient. Would it help if I copy the whole thing? Let's copy the whole thing here so that we can get it. Let's make it green, for example. There's this eternal problem of how to shift things around. Very elegant solution. There we go. We come up here. Okay, good. And let's make this bigger again. It's like this. You don't need to outrun the dragon. You just need to outrun the dwarf. Meaning, I don't need to be your best lecturer with the iPad. I just need to be better than your worst, and you won't think much of it. Okay, good. So where were we? We get the first CI is C0. So this is my C0, this is my C1, coefficients of the initial state. So we get alpha, 0, and now E minus IT over H bar, gamma, P, X, phi 0 X, plus beta 1 e minus I t h bar gamma px 0, which gives us alpha 0 times the x of 0 x minus t gamma. Oh, there was a plus here. Plus this whole thing. Missing a cat x. There you go. Plus beta 1 tensor dx 0 of x plus t gamma x. Let's see if I forgot anything. No, I don't think I did. Okay. So this means precisely that the wave function shifted in the position basis, okay, to the left or to the right. And this is not what we wanted. So remember that originally what we wanted in our case was a shift in momentum. Okay, so we'll just do everything, but because of the relationship between position and momentum is symmetric up to a sign, we just replace wherever we had position, we put momentum and we'll get the right thing. Okay, so this is a shift in position, so we get this to the beta. I'll just draw what we got first. So we got kind of x. We got kind of one here and the other one here, where this area is kind of given by beta square and this area is sort of by alpha square. Okay. Good, but we wanted this to happen in P, in the momentum, not in the position, because we then want the particle to fly away. Okay, but a shift in momentum instead. And this is something you'll do in the exercise class. So we take a new Hamiltonian to be hz, and where before we had the px, now we just put x here. Okay, so this is an s, and this is position. So remember, this first z is the Pauli z. Okay, still. Acts on a qubit, whereas this x acts on the line. Okay. And now this is what you'll do in the tutorials. Is just to apply exactly the same reasoning as we saw before for the modular momentum, and see that what we get when we apply u of t to our initial state is going to be alpha 0, and now hook and shear p minus gamma t p plus beta 1 dp p plus gamma t p. Okay, and now to in order to make sure that these signs are going the way that we wanted, you might need to adjust here the sign of this whole thing. So this is going to be homework to see what the sign should be there so that everything works out. Okay, but the idea is that it's exactly the same. And now we end up with the same plot. Okay. But now, instead of x here, we have px, the attack of x of p. Okay. Good, a few things. What we'll also do in the tutorial is to see how this applies now if we have not just the x, but x and y, but this shift here only acts on x. Okay. And then the idea is that we end up after region B. So let's go back to our original drawing. After this, now we are here. At this point, we make this region really small. So we really just have these two wave functions that are kind of the same in the x region, but they're going in different ways in the p region. So we let them evolve. Of course, they'll spread out, so there could be some overlap. But when you measure here and here, you get the right outcomes, mostly well correlated with the spin of the particle. Okay. And then how do you find out the initial state, this alpha and beta? Essentially, you just measure it many, many, many times. So if you know you can prepare the same initial state many times, you do it, you send it through this whole mechanism many, many, many times, and then you just collect the statistics of measurements. So because you know that the probability of finding the particle in this region is going to be related to alpha or to beta, and vice versa here. Okay. And from here, you can work out the absolute values of alpha and beta. This is still not it only gives you the alpha square and beta square. So what would you do if you wanted to know alpha and beta exactly, if you wanted to know the state exactly? Then you run the experiment again, but here in this region, instead of coupling the variable z, the spin z, now you couple it to the y direction of the spin, and then you couple it to the x direction of the spin. So then you get here's the new probabilities that now depend on the absolute value of these coefficients, but for a different basis. Okay, and when you have then enough bases, so with 3 bases, you can already reconstruct the initial state. And this is one way of doing what we call state tomography, which is exactly wanting to find out what these coefficients are. Now, some caveats. As I said, what happens in reality in this magnetic field is not exactly this this Hamiltonian that we want to implement, but we looked at an ideal case. We've also not looked exactly at what happens in this region. So what happens here, by the way, if we had now only region C, and we thought that we have a state that starts with like this, x and y plus beta 1 to the right, x and y. Okay, we still need to evolve this state and then see what happens to the variable that we want to measure at the end, which is it's going to be x, right? So then we need to evolve it to u of t, which is going to be the identity on S times e minus I t px squared. Squared, right? And so on and so on. Okay, but because this is not going to be a very interesting case of what happens in in region C because they're really going to go in opposite directions. What we'll do is we'll study a more interesting case in which you still have this kind of initial state where you have a superposition of two parts, but now the evolution is such that they're going to interfere with each other. Which in this case doesn't happen so much because they're going to go in different directions. So the interference will be just at the fringes. But we will see what happens in a case where they do interfere, and this is going to be the double slit experiment. Okay, so this is what we will talk about next time. Good. I think we will end up here because, as I said in the email, the re-recording of the other class was 15 minutes longer. So if you didn't watch this now, then you can use this extra 15 minutes to go and watch it. Okay. So let's just write here what we do next time. Next time we will look at free evolution of a superposition. And this is going to be the double slit experiment. Okay. And then after this, we will be done with the free particle for a while. And then we'll look into a particle in a potential that is no zero. Okay. But we already did free Hamiltonians. We looked at non-interacting Hamiltonians in general. Then we looked at an example of interacting Hamiltonian, in particular, one that can be used for measurements. Okay, and then next time we'll look at the double slit experiment. And the nice thing is that we'll use again the modular momentum for this.